In this last lecture, we're going to cover how we provide impedance and force control with our dynamical system approaches. So if you remember in the very first presentation, I told you guys that these really cool properties of dynamical systems, such as like robustness to perturbations and being reactive and adapting themselves to changes in the target or the environment, can be useful for providing passive and compliant interaction for physical human-robot interaction, so as we can see in these videos. And we do this by control architecture, which we call passive DS controller, which is basically a dynamical system-based impedance control law. So what I'm going to talk about at the beginning, the first thing would be this dynamical system-based impedance controller, which we call passive DS. Then I will talk a little bit about how to shape the desired impedance of your task using this controller. And at the end, we will focus on how to extend this dynamical system-based impedance controller to achieve force control as well. So first I'll begin by making a differentiation between using a dynamical system as a motion generator in open loop versus using it in closed loop, as we can see the control loops here. So when we use it in open loop, we basically just initialize the dynamical system, let's say at the onset of motion. So when we have this type of architecture and we have, for example, perturbations in the target or in the environment, which are external from the robot, then the dynamical system still is able to provide this robustness to all of these changes. But if we have, for example, perturbations on the robot arm itself, since we're not feeding back the state of the robot to the dynamical system, this is not it's not capable of being robust to these type of things, of perturbations. However, if we have this type of architecture where we basically close the loop and we feed back the actual state of the robot to the dynamical system, then we are robust to perturbations in the environment, changes in the target, and also perturbations on the robot arm itself. So it must be noted that obviously if our robot is super stiff, so if we're not using a compliant robot, then these two architectures will lead to almost the same behavior because you won't be able to actually move the robot itself. But in all of the applications that we do in the lab and that we envision to have, for example, when we have robots working together with humans, these robots are compliant. So we must use this type of architecture. So the idea is that if we have a dynamical system such as this one, which generates our motion, so if we feed back the state of the robots, then we can have this like passive and interactive behavior with this control law that we proposed, which is basically a proportional action on the velocity error. So here we have the actual velocity of the robot and the desired velocity that's given from the dynamical system. So let's see how this proposed controller acts on the robot. So let's consider these Cartesian space robot dynamics, where Fc is desired control, Fi are the inverse dynamics forces, and Fx are the external forces. This is the centrifugal and Coriolis forces, and also gravity. So here we assume that this vector here is compensating for these two. So what we have is this kind of like reduced model of our robot dynamics. So if we feed in the passive DS control law that we propose, we can see that the closed loop dynamics of the control system lead to something like this, where we can see that the proposed controller is actually just acting on the velocity error itself. So to ensure that we can track the desired motion that's given from the dynamical system while also allowing for perturbations, what we do is we basically construct this is the damping matrix. We construct a damping matrix where its first eigenvalue is in the direction along the dynamical system, and the other its first eigenvector, and the other eigenvectors are basically orthogonal to this to the dynamical system itself. So if we expand this close to the dynamics, we can see basically that what we're doing is, so here we can decompose it into something like this, because the first eigenvalue is actually corresponding to the first eigenvector, which is our dynamics, which are given by our f of x. So what we're doing is basically following the velocity that's given by the dynamical system, and then having some damping values on the directions orthogonal to this flow motion, to the f of x. So for example, if imagine that this is our f of x, like one curve given by f of x, so our damping matrix is basically aligned to the motion given by the dynamical system. So basically the desired behavior is determined by two parameters, which are the damping matrix, here D, and the dynamical system itself. So for example, if we choose lambda 1, so the first eigenvalue, which kind of acts as like the control gain, to 1, and then we select lambda 2 to like 2, we can see something like this. So this is the actual damping matrix. And while we're doing perturbations, we can see how it actually aligns, it's aligning itself to the flow of motion given by the dynamical system. And the values themselves are kind of like the damping values that you would imagine in the classical impedance controller, to basically tell you how much force can be allowed to be like acted upon on the orthogonal directions of the dynamical system. So here we have, for example, another illustration where the second eigenvalue is a little bit higher, so it allows a little bit less perturbations on our orthogonal side, and we can see how it's aligning to our dynamics. Here's another example where we have the inverse. So basically, the main idea is that we have this construction of the damping matrix allows us to dissipate energy in the orthogonal directions of the dynamical system. And another really nice property of this controller is that it offers passivity, and one of the conditions that of offering this passivity is if the dynamical system itself, the one that we're using, has a conservative and a non-conservative term. So a conservative term is basically equal to basically the negative potential function. So if you remember, in the first lecture, in both sets and LPVDS, we learned dynamical systems with the Lyapunov function, so we can actually decompose, if we can actually use sets or LPVDS to generate a dynamical system which provides passivity for this controller. And the proof for passivity is in this paper, so I'm not going to go through that. All right, so here's an example of how this controller works in the real robots. So here's the actual target. The believed target is there, so there's some uncertainty in the targets. And yeah, it's going. So here first, you can see it's basically following a time-dependent trajectory towards the believed target, but since there's some uncertainty, the controller is not really capable of let's say stopping when it senses some interaction forces, because it's not equipped to do something like that. You're just giving it the desired trajectory. While with the passive DS controller, you can see that it's completely passive, so it'll stop when you have some sort of interaction with the environment, even though the dynamical system is still it's formulated such that it will go to another target, but through these passivity properties, it's very compliant and it's passive, while at the same time tracking the desired motion from the dynamical system. Yeah, in this video I think I already showed it many times. All right. So that's quite nice. So we have this controller that is capable of exploiting all of the really cool properties of dynamical system, both in perturbation, so being robust to perturbations on the robot and the environment and changes in the target. So let's see how we can link this to, let's say, the classical impedance controller. So for example, something like this, like an impedance regulator. So we can see that the damping term in our controller is basically the same as the damping term in the impedance in the classical impedance control law. However, what about the stiffness? So what happens with stiffness right here, because we don't really see it? There's no parameter that's called stiffness anywhere in our closed loop dynamics. So the stiffness is basically a nonlinear term that's state dependent, and it's also it's dependent on not only the state but on the dynamical system itself. So, but we can derive it. So if we take the derivative of the closed loop dynamics with respect to the states, we get something like this, where we can see that the apparent stiffness of our closed loop dynamics are basically dependent on the Jacobian of the dynamical system. So it depends on the dynamical system itself times the damping term. So that the first eigenvalue of the damping matrix. So if we want to have a representation of our stiffness, like the representation that we have, for example, of ellipse as a damping matrix, we can derive it using, for example, just deriving the stiffness at a unit norm, following some unit norm with the Rayleigh quotient. So it's basically just extracting a direction with respect to the matrix that we get, which is the Jacobian of the dynamical system. So here now you can see the same illustration, but now with the actual stiffness of the controlled system, where here the stiffness is the pink ellipse. And as you can see, the damping doesn't change, so the structure of the damping doesn't change, it's just aligning itself to the flow, but the stiffness is changing all the time because the dynamical system changes. The way the dynamical system is converging towards the attractor or towards the trajectory changes, or it changes all over the state space. So here we can see how the stiffness is changing over the entire sequence. So that's nice. We have now, let's say, the representation, a notion of classical damping from our controller. We have the notion of classical stiffness. But what about the actual spring-like behavior that this term gives you from the impedance controller? For example, here, this term, which you have like the stiffness times the state minus the desired trajectory, this imposes some symmetry around your reference trajectory, something like this, right? So, can we achieve this with our proposed controller? Yes, but so the only thing that we need to do is we actually need to encode this type of behavior inside our dynamical system. Something like this. So for example, now, instead of the dynamical system just kind of like generalizing the flow of motion towards the target, what this dynamical system is doing, it's actually attracting towards the reference trajectory while at the same time, while reaching towards the desired target. So here, we're having this some sort of like symmetrical, attractive behavior towards the reference trajectory, but at the same time, we're reaching our desired target. So, in other terms, if we want to kind of like shape the stiffness of our task, what we need to do is we need to have a dynamical system like this, which is capable of having these type of properties. So that's what I proposed. So and I proposed this dynamical system, which is called locally active, globally stable dynamical system, which is basically a combination of a global dynamical system, which converges towards like one target, your global target or the attractor, and a set of local dynamics which impose this local different behavior around some reference trajectories through this activation function alpha. So you're basically mixing between a global dynamical system and a set of local dynamical systems. So yeah, so this one converges to the attractor while following different dynamics locally. So here you can see this illustration. So this is for example, this is a global dynamics. It's just it's reshaped such that it follows these trajectories and then it converges to a target. these shaded regions are the activation functions, which we design such that we can say, okay, in these activation regions, we want the dynamics to change locally. We want it to be doing something else. We don't want it to follow the same flow of motion that the global dynamics is following, basically. So here we have, let's say, this set of local dynamics. And yeah, so alpha is there. So if we say, okay, in each of these local dynamical systems, what I want the robot to do is basically go have this like symmetric, attractive motion towards the reference trajectory. So each of these are just basically just different dynamical systems. If we mix all of them together, then we get something like this. So we get this locally active, where different dynamics are activated locally in the shaded regions. But overall, in the entire state space, the global dynamical system is always kind of like, it's always guiding the motion such that everywhere it'll go towards the final target. So what type of dynamical systems can we use? So we can start with very simple. So a linear dynamical system for our global dynamics and a linear dynamical system for our local one. For example, we can have something like this. Let's say here, this is a simple local global dynamical system. And then we impose some local dynamics that converge towards the reference trajectory. So we can have this symmetrically convergent local DS. So it's not limited to that. We can all have some divergent behavior if we want. And also, obviously, we can have nonlinear dynamics because here we're basically just mixing two dynamical systems. So, for example, our global dynamics can be something like this, which is learned through the LPVDS approach, and with following like this C shape. If we activate this local attractive behavior throughout the entire trajectory, then we can have something like this, for example. So this is pretty cool. So how can we ensure actually that this mixing of all of these trajectories is globally stable, and how can we learn it from data? So those are the two questions that we have. So first, to ensure global stability, I use this complex Lyapunov function that I introduced very briefly in the first lecture, which is basically so we have this global Lyapunov function, which is centered on our global attractor, and then we have a set of local Lyapunov functions which are centered which are not centered actually. These are asymmetric, but we impose the asymmetry with the local attractor of our local dynamical systems. So we're kind of like tying this Lyapunov function, this complex Lyapunov function, with our complex dynamical system. So basically, this Lyapunov function corresponds to the stability of this guy, and these guys correspond to the stability of these guys here. So we're tying the Lyapunov function, our complex Lyapunov function, with all of the attractors that we have in our dynamics. And this is just an example of all of the constraints that we need to impose for stability. So for example, all these constraints are for our global dynamics. These constraints are for our mixing functions, and this constraint is for our local dynamical systems, for a set of locally active dynamics. Okay, all right, so now I will describe in a more kind of geometrical way how this constraint is imposing stability. So for example, if we have our linear dynamical system, which is based on this diagonal matrix with negative eigenvalues, we will have a dynamical system that just converges towards the attractor. And the way we generate this locally symmetrically attracting dynamics locally is with this construction of the system matrix 8L, where Q are basically the eigenvectors of this linear trajectory, and the eigenvalues are the ones that impose this symmetrical attraction towards the reference trajectories. So for example, here we have with the same negative eigenvalues, so we don't have any attraction, we just have kind of like a shaping of our dynamics. If we increase the second eigenvalue, we can see that now we have some sort of attraction towards the reference trajectory, and our constraint is still valid. So what this constraint is doing is telling us, okay, your local dynamics, they can converge towards this different towards this reference trajectory, which might lead to velocities which go away from the attractor, but the rate of convergence towards this reference trajectory cannot be higher than the rate of convergence that the global dynamical system has. So for example, here if we increase the second eigenvalue, we can see that there's more symmetrical attraction towards the reference trajectory, and this constraint is still met. But then if we go further, then we can see if we sample some regions around the locally active, if we sample some points around the locally active region, we can see that this constraint is not met. So this is basically how we impose stability in this locally active, globally stable dynamical system. So now, in order to learn this type of dynamical system from data, we have this learning pipeline. So we have some training data which come from demonstrations. Then what we have to do is we need to discover these locally linear trajectories in our nonlinear demonstrations, which include also the local attractors for each local model. Then what we have to do is learn the Lyapunov function, learn the parameters, basically the P symmetric matrices for the global dynamical system and for all the local dynamics. And then once we have all these parameters, then we fit them to this big optimization problem that basically estimates the global system matrices as well as the local system matrix, while being stable. And at the same time, we also have to, so the human has to select what type of locally active behavior you want. So if we have all these components, then we can learn all of this from demonstrations. So here we can see, for example, we have a demonstration of this nonlinear trajectory. Then we extract the locally linear models of the nonlinear trajectory. We find the local attractors and the global attractor here. And then we learn the Lyapunov function. Next, here actually we can see after learning the system parameters, the global parameters and the local parameters, we can see that the system is globally asymptotically stable, as it is negative all around the state space except at the origin. That's where the attractor is, the global attractor is. So here we have an example of just a global part, so just a global dynamics without any local activation. So we can still see the activation function, but there's no local activation. So as you can see, we had with some perturbations, the robot doesn't really follow the reference trajectory; it just goes towards the attractor. On the other hand, if we activate, for example, some locally symmetric behavior around this trajectory, we can see the following. So we started the simulation, the robot is following the trajectory, and once we arrive in this region, which was locally activated, we can see that if we have some perturbations in this orthogonal directions of the reference trajectory, the robot comes back to the reference trajectory, which is basically the behavior that we want, this spring-like behavior around the reference trajectory. So finally, we can also visualize the actual stiffness of the control system. So as you can see here, once we are in this region, the stiffness is super high. It's really, really high on this axis, which is what we wanted to shape for this task specifically. So now we describe different ways of how to represent, for example, damping and stiffness, and how to shape the desired stiffness for the task with our dynamical system-based controller. So what's missing is basically, can we actually control for force? So yes, we can, and that's what will be presented next.